Hello, my name is Elijah Yoder, and this is my research entitled Biomimicry: Fighting Fires with the Power of the Bombardier Beetle, supervised by my advisor, Dr. Wayne Strasser. So the goal of my research is to use computational fluid dynamics to model a fire extinguisher after the defense mechanism of the Bombardier Beetle. The picture on the left shows the Bombardier Beetle using its defense mechanism, and as you can see from the photo on the right, there's the internals of the defense mechanism. So when threatened, this beetle can facilitate a chemical reaction in its abdomen in those two sacs to create a vapor that builds pressure and is eventually throttled, creating a spray that shoots very long distances with a very tight spray. The geometry you see in this photo is the geometry used to try and replicate this defense mechanism. So as you can see in the photo, there's a cylindrical core. That's where a heater would go, a cylindrical heater would go, that is surrounded by a copper sheath. And the little annulus that surrounds that is where the water would flow into and fully encapsulate the cylindrical heater in order to heat the fluid and vaporize it within this metal chamber to create the same sort of mechanism as a defense mechanism of the Bombardier Beetle by increasing pressure by vaporizing a fluid within the chamber that will eventually be throttled out in hopes to replicate the same spray pattern of the Bombardier Beetle. Here are some more photos of the chamber geometry used to model this fire extinguisher. As you can see here, this is the meshed version of that geometry. This is an important parameter in computational fluid dynamics, as various states of the simulation will be calculated at each one of those little nodes where the mesh lines intersect. As you can see, there's important sections marked off for this geometry. So the first simulation that was run using this model was a very crude simulation, meaning that the very bare bones models were used, nothing very complex. And the goal of this was just to essentially get a multi-phase model working and to hopefully build upon that. And so as you can see, the graph on the left shows the maximum fluid temperature inside the chamber, which is around just under 480 Kelvin. On the figure on the right, you see the difference between the heat surface temperature and the fluid temperature as being around 0.375 Kelvin-ish, which is good because it's a very similar number. So here's some more results from the very first simulation. As you can see, the graph on the left shows the ratio of vapor mass flow at the outlet to liquid mass flow at the inlet, which is about 0.35%. This is a very low percent, but what this tells us is that vaporization is happening within the chamber and it is being expelled out the outlet, which is what we want. And the graph on the right complements this sort of graph by showing the maximum volume fraction of vapor within the chamber. And what this tells us is that there are areas within the chamber where the mixture of liquid and vapor is completely vapor, which is to be desired. So here's a contour plot of the temperature of the liquid in Kelvin. And here's a contour plot of the temperature of the vapor in Kelvin. So this contour plot shows the volume fraction of vapor within the chamber. And this final contour plot shows the velocity of the liquid in meters per second inside the chamber. So what we learned from this first simulation is that phase change does occur within the chamber, and we are able to incorporate this into the simulation. However, the model used is very simple, and there are various things that can be improved upon to increase the computational certainty of the model. There are also many other things that can be changed and modified ultimately to optimize the system as a whole. In order to better the simulation, there are various modifications that were employed to see their effects on the results. Those being varying the time step, varying the mesh count, and varying some of the vaporization model settings to see their effects on the result. So here you can see some of the results from the simulation modification. Each graph has color coordinated between the results of each trial. So the graph on the left shows the maximum fluid temperature, and the graph on the right shows the maximum heat surface temperature. Here are some more results from the simulation modification. The graph on the left is the difference between the max heat surface temperature and max fluid temperature. The graph on the right is the maximum volume fraction of vapor. So here are the last of the results from the simulation modifications. The graph on the left shows the total volume fraction of vapor within the chamber, and the graph on the right shows the ratio of vapor mass flow at the outlet to liquid mass flow at the inlet. So here are a variety of contour plots from the various simulation modification trials of the liquid temperature, each with their own labels. Here again are some more contour plots of the various trials, but this time it's the vapor temperature in Kelvin. Again, here are some more contour plots of the various trials, however this time it's the volume fraction of vapor within the chamber. The last set of contour plots here show the velocity of liquid in meters per second throughout the chamber. So what we learned from these simulation modifications is that changing the time step did not result in any significant changes of the model. However, the mesh resolution and all multi-phase settings changes did influence the results significantly, so mesh independence should be studied further and all multi-phase settings should be included in the final simulation. To further study mesh independence, 2 more models were run, this time with a second increase in mesh resolution and a third increase in mesh resolution. So here are some of the results from the mesh independence study. As you can see, the graph on the left shows the maximum fluid temperature for each of the mesh independent study trials, and the graph on the right shows the maximum heat surface temperature of the exact same trials. Again, here are some more results of the mesh independent study. The graph on the left shows the difference between the maximum heat surface temperature and max fluid temperature, and the graph on the right shows the maximum volume fraction of vapor for each of the mesh independent study trials. So these 2 graphs show the last of the results from the mesh independent study. The graph on the left shows the total volume fraction of vapor inside the chamber for each of the models, and the graph on the right shows the ratio of outlet vapor mass flow to inlet liquid mass flow for each of the trials. So here are some contour plots of the second mesh refinement trial. As you can see, there's liquid temperature, vapor temperature, volume fraction of vapor, and velocity of the liquid all within the chamber. So here are some more contour plots of the third mesh refinement trial, again with liquid temperature, vapor temperature, volume fraction of vapor, and liquid velocity all within the chamber. So the goal in a mesh refinement study is to eventually get to a mesh size in which the results from trial to trial don't change. And so what we learned from these trials is that there are significant gaps in the data between each trial, so further mesh refinement should be done in order to get to a place where the difference between trial to trial is negligible. While the mesh refinement studies were occurring, there was another model that was being run in conjunction with those that incorporate a sinusoidal inlet flow rather than just a constant volume flow into the chamber. This is because the theoretical device will have a cycling where water will come in, both inlet and outlet valves will be closed, it will be heated, pressure will build, and then the outlet valve will be open to release the mixture, and then that cycle will be repeated at high frequencies. So the effects of this kind of cyclical process are desired to be investigated, and that was the point of this particular model. So we wanted to know how easy it was to incorporate a sinusoidal flow and vary the flow pattern and how that changes the results of the simulation. So the methods that were used to incorporate this kind of sinusoidal flow was a UDF that was created to create a sinusoidal inlet flow that had an average volume flow rate of 1 liter a second at a frequency of 100 hertz. And then in conjunction with that, there was a UDF for sinusoidal outlet back pressure in order to kind of have moments where the mixture within the chamber was being held inside the chamber from the sinusoidal inlet flow and the back pressure to almost act as the time when both the inlet and outlet valves would be closed to allow for heating within the chamber, pressure to build, and to see how that affects the results. So here's the results from the sinusoidal inlet flow trial. As you can see, the blue graph shows the inlet mass flow. So you can see it's very nice, very sinusoidal, and is exactly what was desired and put in via the UDF. And the orange graph shows the outlet mass flow. As you can see, it's not quite as uniform and pretty, but it is kind of what is desired with the offset from the outlet back pressure flow to create a sort of sinusoidal outlet mass flow. So what we learned from this trial was that a sinusoidal input and output could be achieved within the simulation. However, the actual results of the simulation were not really of interest because this is just a variation of the very first model, meaning that none of the previous iterations and tests of model parameters were incorporated into this, so the results aren't going to be all that accurate. However, this was done to see the ease of which a varying input and output flow could be implemented, and what we found that it could be implemented very easily, and a particular flow pattern could be created based off what is desired. So to build upon the work that has already been completed on this simulation is to continue mesh refinement by using a fourth mesh refinement and seeing if that is the cutoff with which the results don't change a significant amount. And the next step from that would be to incorporate all the previous simulation results with the sinusoidal inlet and outlet flow to see how all of those parameters combined with the sinusoidal flow changes the results, eventually modifying the chamber geometry and the boundary conditions to see if they affect the results at all to create a better flow, and then eventually combining all of these results into one final be-all end-all simulation to hopefully create the most accurate simulation to date. So that sums up the research I've completed in modeling the Bombardier Beetle fire extinguisher. I know I kind of rushed through a lot of those graphs pretty quickly, so if you want me to go back and revisit those and kind of talk through them, I'm more than willing to. If you guys have any other questions, I'd love to answer them. Thank you.